we have a new constraint to worry about, which is that when our rope goes around the pulley, it is non-slipping. Now before, we didn't really worry about what was happening with our pulleys. We simply said, our ropes go around, the pulley spins, whatever, we don't care. Now we actually want to relate what's happening to the pulley to the motion of our object. And the idea being here that we're using the motion along the radius r. And so the speed that the surface must be traveling in order for the rope to be traveling at the same speed relates the angular speed omega multiplied by r gives you the velocity of the rope itself. So the velocity of your object then, v, gets related back to the angular speed of your pulley. If your object is accelerating, then you can relate the acceleration of your object to the angular acceleration of your pulley. So this isn't too hard, but this points to a bigger issue, which is we are now treating our pulleys quite differently. Pulleys now can have mass. Note that I say may. When you get to certain calculations, you should look for information in the problem about whether or not the pulley is ideal, whether it is very light, because it's going to be really complicated to add in that they have mass. You don't want to do that unless you have to. Once a pulley has a mass, you need to identify its moment of inertia. In general, it can be treated as a solid cylinder, though maybe the construction is such that it would better be treated as a hoop. You'll have to be told something about it. So note, if we look over at this extended free body diagram, we're treating the bucket as a particle still. That's fine, the bucket isn't rotating. But we've actually shown that the pulley, what it looks like, that we're modeling it as a cylinder, and now we have to show where the forces are. The normal force is the support of the axle, that's up. There's a gravitational force pulling on the pulley itself, down, but these don't cause any torques because those are right in the center at the axle. The rope then pulls on the side. Now you actually have a torque. And we then would say that the tension here equals the tension here. It's as if it's a Newton's third law pair. But that tells you why that pulley would start to rotate. If that pulley was initially still and you let go of the bucket, there has to be a torque in order to cause an angular acceleration. So the thing to be careful about is that if I had a rope hanging on the other end, that would cause a torque as well. And if we then say the tension is everywhere the same in the rope, now we actually wouldn't have a net torque. So I don't want to go into detail here and make this more complicated than it needs to be, but in many of our old-fashioned pulley problems where we neglected the mass of the pulley, if we actually wanted to take into account the mass of the pulley, tension doesn't actually end up the same everywhere. And the reason for that is that we would actually have to say that there's like a friction force acting along the pulley, and that gets really hard and you get into some differential equations pretty easily. So, this situation, the rope itself is wrapped around the pulley, so we don't have any forces on the other side. When you encounter a rope and pulley problem, especially if it's on the final where you don't know if you need to use chapter 12 material or not, again, look to see if there's any information about whether the pulley has mass or not. If you don't feel like that information is there, make sure to include that as part of your modeling step. If you add in mass and try to take into account the moment of inertia of the pulley when there isn't a reason to, you're likely going to be unable to solve the problem. So, a word of warning there, but now everything is a little more complicated if we want to do this, since we have to think about the moment of inertia of the pulley.